Okay, who can tell me what comet you're seeing there? You got it. And what are the two domes down there? It's Hale-Bopp, 1997. Anybody know what the two domes are? Where am I from? Not Kitt Peak. This is McDonald Observatory. That's our 82-inch and our 107-inch telescopes, which I've spent more than a few nights on, including 3 of them last week. Okay, so this is a NASA image of the 9 planets. Oh, wait. 8 planets. We only have 8 of them. Pluto went away. Well, it's a minor planet. It's a dwarf planet. This is a composite of NASA images, and we actually have a better one of Pluto now, of course. These aren't to scale, but I like to show this picture because it tells me something that's important about it. You see they're sort of in a line. Well, they're not always in a line, but they're all in the same plane, which means they would be going around on the same level. And that's important for our understanding of the solar system. Why is it the planets all go around the sun in the same plane? And that plane is known as the plane of the ecliptic. They also all orbit the sun in the same direction. Now, Pluto's an oddball. It doesn't exactly fit in the plane of the ecliptic. It's tilted by 17 degrees. But all the rest of them, they go around the sun in the same plane, in the same direction. And most of the planetary orbits are essentially circular. All of those facts are clues to the formation of our solar system. So if we go out and we look at some random patch of sky, well, it's not exactly a totally random patch of sky. And this is a visible image taken with the Hubble Space Telescope. And if you blow up and look at this, you see there's a big black area. No, there's not a region of the sky where there's nothing in it. If we take an infrared image, this is what your eye would be able to see. But if we take an infrared image, which is more like heat type wavelengths, you see that all of these things are here that you don't see here. Why do you not see them here and you see them there? Well, it's dust. And there's dust obscuring our view of seeing certain regions of our galaxy and other galaxies. And it's dust and gas from which stars form. So here's a picture of our Milky Way. Hale-Bopp's actually in this picture too, but you can't really see it, and various little things. And I'm going to zoom into this region here using Hubble Space Telescope pictures. So this is the Eagle Nebula, otherwise known as M16. It's a very pretty region. It's a star-forming region. There's a lot of gas and dust in this region. If I zoom in, you see what's known as the pillars of creation. It's also the Eagle Nebula, these beautiful structures that we saw with the Hubble Space Telescope, one of the most famous pictures they made. This is the whiff pic, so it has this funny shape to it. If I keep zooming in, you see there's a little finger, and that is the size of our solar system in that finger. It's tiny compared to the size of the scale of things in our universe that you form suns out of. So we start with a dark cloud. And nothing in space stands still. They're all fidgety. They like to move around a bunch. And they get to turning round and round. Well, if you start taking a bunch of stuff and you spin it round and round, like, have you ever been to the pizza place and they're making the pizza, they're throwing up in the dough and they're spinning it? What happens? It flattens. Right. So it starts to collapse in, gravitational collapse, forms a disk. But pretty soon the star is beginning to pick up energy in the inside. As Chris talked about, we have nucleosynthesis going on, not quite as violently as in a supernova, but it will start to blow things out, the poles. Remember, it's spinning this way. Keeps spinning out, opening up. And eventually you get a disk with the sun inside. The sun actually is burning once it gets to 1,000,000 degrees inside, which it gets to once it's got enough pressure. And eventually you get out of this disk, you form planets. And we now know that planets like Jupiter had to have formed in the first 5 million years of the life of the solar system. The solar system is more than 5 billion years old now. So a blink of the eye and you form Jupiter and many of the other planets. But you have this disk. What happens to the material that's in this disk? Well, it goes on to having to be cleared out or remain as garbage or debris. Well, that's where I come in. I'm a debris collector. And comets are important for understanding the solar system because, like planets, comets orbit the sun, but they don't necessarily orbit in the plane of the ecliptic. So they're not in that plane I talked about. So how do you get them if they're not coming out of this disk and spinning around like that? Well, they have no preferred orientation. Comet Halley, rather famous comet, comes back every 76 years, is actually going backwards in the same plane. Comet Hale-Bopp in 1997 was going perpendicular to the plane, up and down. So they can come from any direction. And what's that trying to tell us? First of all, we now know that they're not circular for the most part. There's one or two, but most of the billions of comets known are not in circular orbits. They're in highly elliptical orbits. For those of you who forgot your math, circle with eccentricity of 0, and as you get more and more elongated, that's an elliptical orbit. And in the case of a comet, the sun might be here, and so it comes very close to the sun at part of its orbit and goes very far away at part of its orbit. So why do I want to study comets? Why am I into debris? Well, because comets are the least altered objects left over from the formation of the solar system. And I said they were there, and now there's things that are left. But parts of them went into building, especially the giant planets in the outer part of our solar system. If we look at the Earth today, and we're trying to understand the conditions 4.5 billion years ago when the sun formed, we have to understand earthquakes, mountain building, storms, oh yeah, life, that peculiar thing that really has an effect on things. All of those things have to be worked backwards. We haven't a clue how to do that. If you think that Chris doesn't know the physics behind what he did, try working life backwards. It ain't gonna happen. So the comets are very simple, and they spend most of their time in the outer part of the solar system, so they're in the cold freeze. So the comets we see today that come into the inner solar system where I get to study them, and I've observed about 200 comets in my career, they come from one of two reservoirs, something called the Kuiper Belt, which is a disk-like region that continues from where Neptune's orbit is, it just continues outwards. It's where we didn't succeed in forming another planet. It just didn't have enough material to form a planet. And most of the objects that are in the Kuiper Belt, this actual disk, were formed there. The Oort Cloud is a spherical halo of comets, which goes out to about 100,000 or more times the distance of the Earth from the sun. So it's way, way out there. They're still bound to the sun. They're still going around the sun, but they're only weakly bound. But they weren't formed there. They were actually formed near Jupiter and Saturn and Uranus and Neptune. And gravity altered their orbits enough to actually throw them outward and form a spherical halo. So this is a conception of what this would look like. This little part in the middle is out to Neptune and all the inner stuff. And then you see the disk, which is the Kuiper Belt. And then you see this big, huge circle. Well, that actually comes out of the plane towards you and all. It's a big sphere. And that's the Oort Cloud. And there's probably much more than 1 billion comets out there. And these things are left over from when we formed our solar system. They are the debris. So what do they tell us, and what are they? Well, they're dirty snowballs. Now, in Austen, you probably don't know much about snowballs. We only get ice. But if you've ever been where they go and have snowballs, that's what they look like, except that they're kind of different. They're a mixture of dirt and ices. So when I use the term dirt, everybody goes, what do you mean by dirt? Walk out the door, bend down, in the garden, pick up the dirt. That's dirt. Nothing more sophisticated than that. It's also ices. Now, you think ice, you think water ice. Well, 80% of them is water ice, but there are other ices, dry ice, carbon monoxide, carbon dioxide, ethane, formaldehyde, methane, ammonia, methanol. Oh yeah, there's the alcohol I love. But all those things, 50% of the mass of the nucleus is dirt. So they might not be icy, dirty snowballs, they might be icy mud balls. Same thing. And they're tiny. And that's why they don't have earthquakes and mountain building and life. Because they're typically a few kilometers across. You could plop it down on the top of the Capitol and it wouldn't even go all the way down to the southern end of the town or the northern end of town. They're little. Halley's nucleus is about 16 by 8 by 8 kilometers across. So that's 10 miles by about 5 by 5 miles across. Borrelly 8 by 4 by 4, and Hale-Bopp, which is a big guy, is 25 kilometers across. It almost goes end to end on this city. So how do we know this? Well, we have ways we can measure, but we've also had flybys. And they started in 1986 with Comet Halley. This is a picture from the Giotto spacecraft, which was a European Space Agency one. One of the little embarrassing secrets about this one is we expected ice, bright. We're going to lock in on that bright spot and we're going to follow it as we come in. Only problem was that's a jet coming off of it and the nucleus is actually dark. And by the time they got close, if they hadn't been knocked off course, they would have pushed the nucleus out of the field of view and only been imaging the jet. Oops. Stardust spacecraft went past VILD 2. Borrelly was actually before VILD 2, so Borrelly was the Deep Space One spacecraft. This was Deep Impact, where they actually crashed a little spacecraft into the comet to see what it would do. I didn't think that was funny. I thought it was great. And Hartley 2, which was this spacecraft reused. This spacecraft got reused and looked at this guy again after the impact. One of the weird things, do any two of these look the same? They don't look the same to me. They all look different. They're not only different sizes, they're all different. And there are funny features on it. This guy's real soft and looks, you know, like nothing's sharp on it. But this guy, see this big flat area? When we first saw this image, we said, oh, it's a depression and it's filled with ice. Only problem is when we started measuring it, that's not a depression. That's the top of a mountaintop. That's a flat mesa. Oops, how do you get that? We don't know. See this sharp crater here? Why is there a sharp crater on something that's icy? The impact from the spacecraft was right there. I've never seen the crater. I don't believe it's seen. You can see it looks like there's been two pieces stuck together. It's all really bizarre. What are we looking at? We don't know. This guy is really kind of cool. So we get these images and we ponder what they mean. And these were all flybys. So they went past, zoop. They're past, they're done. A few hours, that's it. Well, as a comet approaches the sun, it's heated. And in the low pressure of space, the ice doesn't go to liquid. If I took an ice cube and I put it out here, you'd pretty much soon have a puddle of water. But if I put it in space, you're going to have gas because it's called sublimation. It transfers directly to the gas stage. And that's what then makes it so that we can see the comet and really enjoy it. The little nucleus is so little, it has so little gravity that the gas escapes outward from the nucleus. I went to a briefing with a bunch of engineers who were trying to plan a mission, and we kept telling them, no strength, no gravity. They kept looking at us, shaking their heads. What do you mean, no strength, no gravity? It's a comet. No strength, no gravity. Can't be. No strength, no gravity. They don't. They have essentially no strength and no gravity. The escaping gas carries with it some of the dirt. Remember I told you that 50% of it is this dirt stuff. So it forms an envelope around the nucleus, which is called the coma, and that's what I see from a telescope. I can't see the nucleus from the telescope because that silly coma gets in the way. Besides, the nucleus is too little to see from a telescope. So the coma obscures our view of the comet. If you notice in those pictures, none of them look like icy surfaces. They didn't exactly look bright and shiny. That's because we see no ice on the surface, or almost no ice. They're almost totally black. See this black cloth? It's as black, or the comet's actually blacker than that black cloth. Pretty impressive. Oh, incidentally, the moon is black too, but you didn't notice that either. So this is Hale-Bopp again, showing you the parts. You have the nucleus buried deep inside the coma, a dust tail, so that's the dust coming off. It's pointing directly away from, it's following in the orbit of the comet. And this is the ion tail, so that's gas that's been ionized, and it's pointing directly away from the sun. I just figure, you're talking about comets, you got to show you pictures of the most beautiful things in the solar system. So there's been another mission recently. This was the European Space Agency's mission called Rosetta. Went to a comet called Churyumov-Gerasimenko. Yes, we have to learn how to pronounce weird things, otherwise known as 67P CG. And this is the approach images. And the thing is rotating very clearly, and it doesn't look round. As a matter of fact, it's the rubber ducky. That's what they called it. And they were going to land a lander on this. How do you land something on that? A lot of chutzpah. Well, they tried. When they released it from the main spacecraft, the lander is called Philae. When they released it on 12th November, they knew that the harpoons that were supposed to attach to the surface were not working. But what else? You're there. You might as well let it go and see what happens. It was a surprise. So it came down and it landed there. You can see it coming in. I mean, it's coming in there. And then a little later, it's now, the comet's rotating underneath it, so it's now over this spot. And you can see it there, and then it's not there. There's footprints. This is before. This is after the touchdown. There's footprints. Where's the spacecraft? Did it vaporize? No, it took off from the surface. There is no strength and no gravity. And it flew for another couple hours, and it landed again. And then it bounced off the surface, and it landed again. And it bounced off the surface, and it landed a fourth time and settled. Yay! We couldn't find it. It only talked for a couple of hours, and then it ran out of its battery, and though it had solar panels, they weren't in the sun. Well, if I go back one, you see this thing? Where would you put the damn thing if you wanted to hide it from the sun? You would put it under in that crevice there, and that's where the thing finally ended up. But we didn't know that for a couple of years. They kept looking, and they kept, as they came into the sun with the comet, because they stayed with the comet for several years, they kept looking where they thought it landed, and finally, that's the surface. Looks like ice, doesn't it? No. It's under there, and there it is. That's this spot blown up. That's the leg of Philae. They talked to it briefly for about half an hour at one point. That's the only power they got out of it. Oh well, space is not a given. So what have we learned? We've studied lots and lots of comets, and we've learned they have very little gravity and very little strength. I told you that already. 70% of the comets look very similar composition. So great, that tells us all about how the solar system formed because we can get the chemistry. Oops, 30% look completely different. And we don't know why. There's nothing obvious. It's not one type. It's not all from the Oort Cloud or all from the Kuiper Belt. We should have stopped when they were all from one region, and then it would have been easier. We know it's not due to subsequent evolution of the nucleus because of other information. Most of the molecules we observed were formed in the solar nebula, so in the cloud of gas that was forming our sun, but some were formed in the pre-solar nebula, in the interstellar clouds. Some of the dust in the comet has to have been very close to the sun because it's been heated very, very hot, which tells us there's been a lot of mixing in the early solar nebula when you form planets. And while comets are icy, then they might have delivered some of the water to the Earth. The details of the comet composition show the comets were probably not the major source of Earth's water. And so we go on to try to learn more and find out what are they telling us about the origins of our solar system, because if one thing we always want to know is where do we come from? Thank you.
All right, thank you, Comet Chameleon. Okay, we'll take some questions from the audience. All right up front.
Did you mention where all that dirt came from?
Oh, it's just part of
the microphone.
Oops, sorry. Where did the dirt come from? The dirt came from that cloud that you saw in those pictures. There's dirt mixed in with the gas in those molecular clouds. There's dust everywhere in the universe. It's not a good housekeeping situation.
All right, other questions? Gentleman right there, yeah.
You mentioned that the comets in the Oort Cloud originally started near Jupiter. What kept them from leaving the solar system altogether?
Good question. What kept the ones that are near Jupiter when their orbits were changed from leaving? Well, actually nothing for about 90% of them. 90% of the comets were thrown free. About 10% are left. That's still 100 billion comets.
All right, more questions? Right there.
It's light reflecting off the dust mostly. Some of it is light fluorescing on the gas, but most of what you see with the white part is the dust reflecting light.
All right, more questions. Let's go in the back. Sir?
Yes.
Repeat the question.
I did. We measure things in what we call albedo, which is the amount of light that is incident upon something and how much comes back. About 6% of the light that hits the moon's surface reflects back. That's pretty damn black. And it may not look black because it's so close and the sun is there and it illuminates it so well, but it is black. And so if you ever go out to, say, Hawaii or any place else there's a volcano, look at the lava. That's the same stuff that the moon is made of. It's black. And it scatters.
All right, I'll take your raised eyebrows as that was a good answer. All right, also in the back.
Well, as I said, the nucleus is a combination of ice and dust. So the ice is 80% water. About another 5 to 10% is CO2 and CO. And then all the other things you add in is methane, ammonia, formaldehyde, methanol, ethane, acetylene, on and on and on and on, things we haven't even measured yet. The dust itself is, as I said, just like dirt. So it's silicates and olivine, pyroxene, all sorts of normal minerals.
All right. Question right there.
So the question is, if the gas and dust keep coming off, can the comet die eventually? Yes, it can. We think that the end state of comets is one of three things. One, its orbit just gets changed so it's thrown clear. So it disappears. Another one is it's sending off so much stuff that there's essentially no more icy materials that can be sublimated, and therefore you won't get the coma and you won't see it very much. Or you might get a burble of material. And we have things that are very inactive comets. The third possibility is, as it takes off some of this dust with it, some of the dust is relatively large. And as little gravity as there is, some of it actually can fall back onto the comet and seal it up. Now, we don't know which one is exactly the right answer, but we know that the lifetime of a comet is in the inner solar system is probably somewhere around 10,000 years. And then something happens.
Always wanted to know that. Thanks for asking that. All right, other questions? All right, there.
I would say it's probably pretty high. We do know by looking at white dwarfs, which are stars that are much older than the sun and they're sort of cooling off and dying off, that we see evidence of things falling down on the surface, and that's either asteroids or comets. So rocky materials, we do know that there is evidence. There has to be, we see disks around forming stars, so there has to be the equivalent of comets and asteroids on all of these systems at some point in their lifetime.
All right, I had a question upper deck. Outside voice, sir.
You see 200 comets. What was your favorite one and why?
Well, one doesn't want to pick between one's children. I think my cover slide probably tells you it's Hale-Bopp, because Hale-Bopp was just magnificent to observe, trying to understand the science. It came at the right time. We had a lot of new equipment had come on in the last half decade, and so we learned incredible amounts about comets from that comet. Now, if we hadn't blown up the comet mission I was part of, which was the Contour mission, I probably would have been one of the ones we went past, but we didn't get to go past because we blew up after 6 weeks. But it's got to be Hale-Bopp. It was a magnificent comet, but there'll be more like it eventually.
All right, one last question. Last thing you could ever ask about comets. All right, if not, I'm going to ask. There we go. Thank you.
Okay, what is the difference between a comet, a meteor, and an asteroid? And I've kind of dropped asteroids into the conversation. So asteroids are also debris left over from the formation of the solar system, but they're almost entirely rocky. There's a little bit of icy material. They exist in the region between Jupiter and Mars. So the reason they don't have a lot of ice is because they were warmer. So again, they're debris, but because of Jupiter's influence, they're actually more altered than the comets are, which is why we prefer studying the comets. The comets stay much more pristine. A meteor is basically, well, you have meteor, meteorites, meteoroids, all those things, but a meteor is something that actually enters into the Earth's atmosphere. It could be a piece of comet, which was the Tunguska event in 1908, or it could be a piece of rock, which is an asteroid. And it's a meteorite when we actually can collect it off the ground and put it into our specimens and measure it in our labs. So it's something we were actually able to, and almost none of those are comets because comets have no strength and no gravity.
All right, let's thank Comet Chameleon one more time.